In this video, I'm going to speak about the solution to the Monty Hall problem and why the explanation given in the movie 21 was misleading, and of course you shouldn't trust movies to teach you math. So if you haven't heard of the Monty Hall problem, it goes like this. There are three doors, and one of them is randomly chosen to hide a car, and the other two are going to hide goats. So you choose the door, and if you choose the door with the car, then you win the car. And if you choose one of the doors with goats, presumably you win nothing. Right? So let's say you choose door 1. So the twist in this problem is after you choose the door, Monty is going to open, that's the game show host, is going to open up one of the other doors. Right? So he's never going to show you your door, and he's going to open up one of the other doors with the goat. And you know that in this case, if you chose door 1, you know that door 2 or door 3 is going to have a goat, right? That's going to be one of the doors he shows you, because if the car was behind door 1, well, then there have to be goats behind doors 2 and door 3, so he could show you either one. If your door hid the goat, right, so if you chose the door with the goat, well, there's still one other goat in doors 2 or door 3, and so he'll just show you that one. So after he shows you the door with the goat, he asks, do you want to switch? And if you switch, and your switching would make it so that you actually choose the right door, so in this case, if you switch to door 3, and then door 3 is the car, well, now you win the car, right? And if your original door had the car, then you would lose, right? So do you increase your odds of winning if you switch? Or does it just stay the same? So the misleading explanation from the movie goes like this. The professor says, well, how do you know he's not playing a trick on you, trying to use reverse psychology to get you to pick a goat? And the student's like, well, I wouldn't really care. My answer is based on statistics. And then he says a little more, and then the professor speaks. And then the student says, when I was originally asked to choose a door, I had a 33.3% chance of choosing right. But after he opens one of the doors and re-offers me the choice, it's now 66.7% if I choose to switch. So what is he getting at there? Well, initially you had a 1/3 chance of getting it correct, right? And you had a 2/3 chance of getting it wrong. So given that you got it wrong, it's going to be either behind, the car is either going to be behind doors 2 or door 3. Right? And Monty just showed you that door 2 had the goat, so if you got it wrong, you know it has to be behind door 3. So in the 2/3 chance that you got it wrong, right, the car is going to be behind door 3. So if you just switch to door 3, right, you'll win the car. And the 2 out of every 3 times you were wrong, right? So it seems that your original door stays at probability 1/3, and the other door, in this case door 3, now has a probability of 2/3 of being right. Right? But this is not necessarily the case. Monty can actually make it a 50-50 proposition. So this thing about where the professor says, how do you know he's not playing a trick on you? Well, based on what he chose, right? Based on how he chose, maybe he is trying to play a trick on you, right? Like, it's not necessarily the case that it will stay 1/3 for the original door and 2/3 for the other door. Of course, as we're going to see, it's not going to be worse by switching, but we'll get to that. So a professor in college told me, or just told the class, he said, probability is about information. So if your probability is going to change, it means you had to have learned something new. Right? So the proposition here in this movie, or the assumption here in this movie is, look, you selected door 1. You already knew one of the other doors had a goat. Right? So he's just going to show you one of the other doors has a goat. And as far as learning new information about door 1, whether that had the car or not, if he just shows you it's door 2 or door 3, does it really matter? Right? And if it doesn't matter, if he hasn't really given you any new information about your door, whether it was correct or not, then it should still have probability 1/3. Whereas the other unopened door, in this case door 3, why didn't he show you door 3? Right? Was it just random chance? Or was it because he couldn't since it concealed the car? So you potentially learn something new in the scenario that they're sort of alluding to. You potentially learn something new about door 3 because maybe he didn't open door 3 because it concealed the car, right? Because he did have an option of showing you door 3. He didn't have an option of showing you the door that you chose. Okay, so let's analyze this a little more formally, right? So here's the sample space, which is going to be the set of all possibilities that I drew in a table here. And so you can see that there are 3 possibilities where the car is, right? So the car is either behind doors 1, 2, or 3. And then Monty can open door 1, 2, or 3, right? And so these are all the possibilities. So for instance, this represents this over here represents the car being behind door 1 and Monty opening door 2, right? So both of those things happen. So let's actually talk about the probabilities. Let's actually figure this out by filling in the table. So initially, the probabilities that the car is behind door 1, 2, or 3 are all the same. So we're going to say it's all 1/3. And just to give a little more intuition behind this, let's just say that there were 90 times where we played this game, right? So if 1/3 of them, the car was behind door 1, 1/3 the car is behind door 2, and 1/3 the car is behind door 3, right? Then that would mean that we have 30 times the car would be behind door 1, 30 times the car would be behind door 2, and 30 times behind door 3, right? So we also know that Monty is not going to open door 1, right? So we're assuming here that you selected door 1, so he can't open door 1. So the car being behind door 1 and Monty opening door 1 is never going to happen. The car being behind door 2 and Monty opening door 1 is still never going to happen. And the car being behind door 3 and Monty opening door 1 still never going to happen, right? So each of these have a 0% probability. And again, it would be 0 times that this occurs then. Right? And Monty is not going to open a door with the car. So if the car is behind door 2, Monty is never going to open door 2. And if the car is behind door 3, then Monty is never going to open door 3. Right? So again, these are just zeros. Now, if we're again saying like 30 times for each of these, then we can actually look at this and say, well, these have to add up to 30, right? The car being behind door 3, break it up into 3 cases. The car is behind door 3 and Monty opens door 1. The car is behind door 3 and Monty opens door 2. Or the car is behind door 3 and Monty opens door 3. So if the car is behind door 3 30 times and Monty can never open door 1 or door 3, right? He has to show you door 2 when the car is behind door 3. He can't open your door. So the 30 times that the car is behind door 3, right? Monty will open door 2, all of them, right? So this also has a probability of 1/3. And similarly, when the car is behind door 2, right, Monty is going to have to open door 3. So this probability is 1/3 as well, right? So again, 30 times that the car is behind door 2, and all 30 of them, when the car is behind door 2, Monty is going to be opening door 3. Right, so now let's get to the interesting case, which is when the car is behind door 1. So remember, when the car is behind door 1, Monty has a choice of whether to show you door 2 or door 3. Right? And let's say, and this is the hidden assumption, that he flips a fair coin when there's a choice. So we expect, half of them to be heads, half of them to be tails. So basically, of the 30 times when he opens door 1, of the 30 times when the car is behind door 1, right, 15 of them Monty is going to open door 2, and 15 of them Monty is going to open door 3. So if you see, this is 15 out of 90. This is 1/6 of the time. So the probability that the car is behind door 1 and Monty is opening door 2 is actually going to be 1/6. And similarly, the probability that the car is behind door 1 and the Monty opens door 3 is also going to be 1/6. And you could also just look at this as 1/2 of 1/3, right? So half of the time that the car is behind, half of the time that the car is behind door 1, which happens a third of the time, he's going to show door 2, which means that a sixth of the time, right, half of a third, a sixth of the time the car is behind door 1 and Monty opens door 2. So now let's think about this scenario, what the probability of switching would be. Well, in this case, you could do the math on this, right? And if you do this formally, this means we're using C1 to mean that the car is behind door 1, and we're using D2 to mean that Monty opens door 2. And so if we said the probability that the car is behind door 1, given that he shows you door 2, you could say, I mean, this is the definition of conditional probability. It's the probability that both of these things are true, right? So the intersection of these two events divided by the probability that of the given information, right, that he shows you door 2, right? And the probability that he shows you door 2 could be broken up into the 3 probabilities, right, over here. Monty opening door 2. So the probability that Monty is going to open door 2 can be broken up into the probability that Monty opens door 2 and the car is behind door 1, Monty opens door 2 and the car is behind door 2, or Monty opens door 2 and the car is behind door 3. And of course this middle probability is 0, so we don't include it, and so we just do the probability of the car being behind door 1 and Monty opening door 2 plus the probability that the car is behind door 3 and Monty opens door 2. And again, if you do the math of this, you will see that it comes out to 1/3. But it might be a little easier to understand if you just look at this column in this table and you see, of the 45 times that Monty actually showed you door 2, 30 of them the car was behind door 3, and only 15 the car was behind door 1. So what that would mean here is that the probability that the car is behind door 1, given that Monty opened door 2, is 15 out of 45, right? We only consider the 45 times when Monty is opening door 2, and on 15 of them, the car was behind door 1, right? So it's 15 out of 45, which is 1/3, and the other one, car being behind door 3, was 30 of the times that Monty opened door 2, right? So it's 30 over 45, or 2/3 is the probability, right? So this was twice as likely as this, and these probabilities, since this is 0, these probabilities have to add up to 1, right? So if this is twice as likely, this has to be 2/3, and this is 1/3, right? So this is really what's assumed in the movie, that Monty is going to choose randomly between door 2 and door 3. He's equally likely to select these doors when he has a choice. Okay, so let's consider, though, another possibility. Let's say, in this case, now Monty is always going to choose door 2 when he can, right? Well, in that case, the probability of sticking with door 1 is the same as the probability of switching to door 3, right? So we could see this as follows. When the car is behind door 1, he's going to open door 2, right? He can open door 2 because the car is behind door 1, so we know that there's a goat behind door 2. And in this case, in the 30 times that the car is behind door 1, all 30 of them, he's going to open door 2. He's never going to open door 3, right? So this has probability 0. So now when we look at this column here, right, we see when Monty's opening door 2, 30 of those 60 times, in this case it's now 60 total times that Monty is going to open door 2, and 30 of them, the car is going to be behind door 1. So the probability actually is a half, right? So the probability that it's, that if you don't switch, or the probability if you switch of winning, they're equal. They're both 1/2, right? And again, you can do the math to see this works out. So really, again, it goes to whether we got new information or not. In the first case, where Monty's flipping a coin to determine which door to open when he has a choice, you're not getting any new information about your door, right? You knew that one of the other doors had a goat, and he was just sort of flipping a coin to decide which one to show you, right? So your probability that it's behind door 1 does remain 1/3, and you should switch, right? Because then your probability that you'll be right is 2/3. On the other hand, if Monty is always opening door 2 when he can, then the question really becomes, was he forced to because door 3 had the car, or was it because he could now choose to do that since your door 1, your original door 1, had the car? So now he's not choosing randomly. Now he's basically saying, I'm going to show you door 2 whenever I can. So if he shows you door 2, it's possible that he was showing you door 2 because your door had the car, right? And he wasn't doing it by random chance, right? So it's really in this case where door 1 and door 3 were equally likely to hide the car, right, before he showed a door to open, right? And if door 1 has the car, he's going to show you door 2. And if door 3 has the car, well, then he has to show you door 2, right? Because he can't show you the door with the car, and he can't show you the door that you originally opened. But the point is that each of these choices was equally likely. And in both of those cases, these are the only cases where he's going to show you door 2. And as I said, these are equally likely choices here. These are equally likely outcomes here. So the probability that it was actually door 1, that your initial choice was right, is actually going to increase to 1/2. Right? You did potentially learn some new information about your door. So in this case, when there's a 3-door scenario, it can only help to switch, but it might stay the same. The probability might stay the same. So it can go up to 2/3, or it can stay at 1/2, but it can't be worse than 1/2, so you may as well switch. Right? And this really actually gets to sort of an interesting extension of this, is that could you cheat, right? Like, let's say you and Monty, I mean, the movie depicts it as Monty's trying to get you to lose, but what if you had some, like, or you as the contestant had some sort of deal with Monty about cheating, and he was going to help you win? Well, when there were 3 doors, he really couldn't help you to cheat, because if he wanted to say, look, I'm going to give you this tell, whenever I show door 2, you know that your door had the car, right? Well, if he did this, then we actually saw that that would make it worse, because now whether you choose door 1, stick with door 1 or switch to door 3, your probability is 1/2 in both cases. Whereas if he had just flipped a coin to decide whether to actually, whether he's going to show you door 2 or door 3 when you selected the car, with that strategy, you would actually have a 2/3 chance of switching, right? So in this case, it's better for Monty to just play by the rules. Of course, he should be honest anyway, but I'm saying if you were trying to cheat. But the 4-door case is a little more interesting. If there were 4 doors and 3 goats, now he could choose to show you door 2 only when your door hid the car, right? So if you selected door 1 and it hides the car, he's going to show you door 2. If you select door 1 and it doesn't hide the car, then he's going to show you door 3 or door 4. Right? So he can do this because there are 4 doors. So in this case, if he shows you door 2, he's telling you your door has the car, so you shouldn't switch, right? So in this case, it actually would be advantageous to stick with your initial door, because you'd have a 100% chance of winning. Right? And just to sort of illustrate this point, let's say, again, you chose door 1 and your door has the car. Well, Monty's going to open door 2. That's his way of telling you selected right. You selected correctly. Now, if your door had the goat, right, and let's say the car were behind door 2, well, Monty can show you door 3. Right? if the car were behind door 3 and your door had the goat. Now originally in the 3-door situation, he would be forced to show you door 2. So like when he shows you door 2 with this tell, you don't know if it's because he has to show you door 2 because door 3 had the car, or if he was actually trying to tell you, hey, your door has the car. But with the 4-door situation, he doesn't have to show you door 2 anymore, right? So he's saying, look, your door was wrong, so I'm going to show you door 4. And similarly, if the car were behind door 4, he could just show you door 3, right? So I just wanted to show you that there's an example